Okay, so what is a quaternion? It's a 4D vector. All right, Q as the quaternion, it can be written as Q0 plus QXI plus QYJ plus QZK. Now we are used to vectors, right? We have unit vectors I, J, K, the same thing over here. There's a component X, Y, Z, but then there's this fourth term Q0, which is the constant term, which is not, it's a scalar basically. Now there are various ways of writing of the quaternion, various ways of writing Q. I'm going to give you a few ways. One is you could write Q as Q0, indicating the constant part, and then just put a vector sign indicating that's a vector. So it'll be QXI, QYJ plus QZK. Another way people write this is they'll say the real part of Q is Q0, and the imaginary part of Q. Okay, so complex numbers, we usually have X plus YJ. So imaginary part is here refers to the vector part. That would be Q vector. You could also write as QX, QY, QZ, and we like to have column vectors, so I put a transpose there. Another way to write this, and this is going to be useful in this course, is to write it as a vector like this, Q0, QX, QY, QZ. Okay, so one thing which we'll need is the conjugate. Think of that like, the transpose is like a conjugate for matrix. Conjugate here is, so the conjugate of Q is denoted as Q bar. It's Q0 minus Q bar, Q vector. So just take the vector part and then put a negative, and that's the conjugate of Q. Okay, so the other thing is the norm. The norm will use the same notation we used for other things, that is two straight lines. Q0 square plus QX square plus QY square plus QZ square. Okay, and one more thing which will be very important, we'll be using this somewhat in this course, is the quaternion product. You could multiply two quaternions together, and there's a formula for it. I'll write it down. So it's denoted by Q dot P. Okay, so Q is a quaternion, P is another quaternion. So let's say it has P0 for its real part and P vector as for the imaginary part. So you could write it as Q0, Q vector, dotted with P0, P vector. This comes out to be Q0, P0 minus the dot product of P and Q. So that's the scalar part. And then for the vector part, it's Q0 P vector plus P0 Q vector plus Q cross P. So this is the dot product which we use in vectors, right? You take the components and multiply them. And then this is the vector product. Okay, so that formula is important. And there are other formulas about quaternions, which I think, well, there's the people who use quaternions for other things, and they are interested in those things. But for us, the only things which are important are these three things: conjugate, norm, and quaternion product. That's it. Now, the quaternion by itself, I don't know of any good geometric interpretation of the quaternions the way it is set up. Okay, so the way you can link quaternions with Euler angles, sorry, with rotations or uh, with rigid body dynamics is through what is known as the axis angle representation. So there's another way of representing rotations, and we'll connect that axis angle with quaternions. So quaternion is good because the math there can be useful. And the axis angle is how you connect it. So let's look at the axis angle representation, and then we'll connect that with quaternions, and that will connect with the bigger rigid body rotations. Axis angle representation. Okay, so let's say that we have a vector x, and then we rotate it x bar. Right, this is what will happen, right? If you take any rigid body, you draw a line on that rigid body, like one of the sides, and you rotate it, the object, that side will rotate. So that side is x here, turns to x bar. Now, it turns out there's a way to represent this rotation by looking at rotation about an axis. I'll call that n hat. I'll connect that n hat with x and x bar. And then this angle, let's call it psi. Not psi, it is phi. Not phi. Let me write down a few things so that you'll remember this. So vector x rotated to x hat. This rotation may be expressed by a unit vector n passing through the origin, like I shown here, that O there shows the origin. And an angle psi as shown in the figure. Okay, so what this is saying is that any rotation, like if you take x and you rotate to x bar, can always be represented by a unit vector n passing through the origin and an angle psi as shown there. Okay, always. So this n psi is the axis angle representation. Okay, so that's just the theory. Now, there is actually a formula which you can derive from this equation, from this figure, which I will not get into. If you're interested, send me an email. I'll send you the reference to the derivation. There is the formula which you can write for the rotation matrix R based only on n and psi, and I'll put that down, and then we'll just be good users of that. We will not really derive that in class. So what we'll do here is we take the axis angle, that is n and psi, and I will give you a formula which gives you the R. So that arrow direction means that given n psi, I will give you a formula for R. So if we can write, if we have x equals R times x bar, then this R is given by identity plus sine psi n, and I'll write down what n is in just a bit, cosine of psi n square. So N is the skew symmetric matrix N, Z, Ny, and Z0, Nx, Ny, Nx, 0. Okay, so if N, the vector N can be written as Nx, Ny, and Z, then you can create a skew symmetric matrix. A skew symmetric matrix says that if you take the matrix N, add it to the transpose N transpose, then you'll get 0, right? So that is a very useful relation. You can always take a vector N and write it as a skew symmetric matrix. In fact, I don't know if you did homework 1, you should see there was a question on this. I believe I put a question where you did the A cross B and converted that to a skew symmetric matrix A times P. It gives the same answer as A cross P. Okay, and the N square is nothing but N times N, just square of that. So it's N is a matrix now, and you can take the square of the matrix. If you wanted to compute R transpose, it's actually pretty straightforward. You just use this formula. You actually just need to take the psi and make it negative psi. So you get this formula. Here it is X bar is R transpose X. Okay, so this formula is actually also known as the Rodriguez formula. For rotation. I think we should write it as Rodriguez. Okay, so you might have heard of that formula, Rodriguez formula. That's pretty much that. Okay, so we've basically shown how to compute if you're given N and psi, then this shows how to compute R. Okay, now this is something which we will not do. This is complex. That is the reverse one. There are ways to compute that. Actually, the way to compute N psi would be first from the rotation, we'll get the quaternion. And from the quaternion, we'll get N and psi. So we'll never take this route. This is, it's going to be pretty complex because what will happen is R would have 3 cross 3, and then you'll have to expand that out and write Nx, Ny, and Z and phi. So you'll have 4 unknowns on the right side, 9 unknowns on the left side, and there are constraints, and just going to make your life hard. So we'll never do that. We'll actually go through quaternions. The way to do this is we go from R, we compute quaternions, and then from there we compute that. That's the route. We'll not take this direct route. But this route is straightforward. I just showed you how to write that. Given N psi, you can compute R. Okay, so that gets us to the next part, which is how is quaternion connected to N and psi? Okay, so this is how they are connected. So here what we're going to do is take the quaternion. Let's call that Q. And then we'll show that you can actually compute axis angle. But you can also go the reverse direction. It's super easy. You could do either way, back and forth. So this is how it is done. So Q0Q is nothing but cosine psi divided by 2 sine psi divided by 2 times n. That's it. So that's the relation between quaternions and axis angle. Super simple. The constant part is cosine psi divided by 2, and then the vector part is sine psi divided by 2 times n. Note that it's half of the angle. Don't take the half outside. That's incorrect. So we can do it both ways. Let's say given one can compute okay, so we are given the quaternion, we are asked to compute n and psi, which is the axis angle. Now it's easy to see that if you look at the equation there, if you are given the left-hand side, q and q vector, if you are told to solve for psi, the formula is psi. First we'll solve for psi, take this, equate it to q0. So that would be twice cosine inverse q0. So once you found psi, you know the numerical value, you can equate this part to this part, and then you'll see that n is sine psi divided by 2. So let me just write it as n hat, no, sorry, q bar divided by sine right. So sine psi is known because you already computed in the first step, and then you can find n. The other one is given n psi, one can compute q0q, which was the formula earlier, as follows. q0 is simply cosine psi divided by 2, and q hat or q bar, q vector is sine psi divided by 2 times. Okay, so you'll basically, this is very handy to write code which will do these conversions, because you'll see that sometimes it's good to stick with quaternions, sometimes Euler angles and so on. We'll never really use axis angle, but I'll test you on some questions in the homework, but normally it is just the quaternions. So first we want to do quaternions rotations, right? How do you do that? Well, it turns out that if q is the quaternion, and remember x was that vector I showed you, that thing x equals q quaternion product with x bar q conjugate is actually the same as x equals r times x. Okay, looks weird, but that's how it is. You can actually show that that is true by using well, x here is a vector, so it'll have a 0 constant part. You can actually derive that expression by putting that value, and then you can use the axis angle to show that. I will skip that, but remember that rotation with quaternion world is q x bar q conjugate. Okay, with that you can actually expand out q. So take that formula here, and then use the quaternion product, something I told earlier, and then you can actually write down this rotation matrix. It has q's all over the place, but you trust me, you never have to, once you write a code for this, you never have to bother with this. Just call it, and then you'll get the rotation matrix. So given q0, qx, qy, qz, you can find rotation matrix. This is how you do it. Okay, so this is very straightforward, right? It's easy to do it. Now, if you do the reverse calculation, that is a bit messy. So given the rotation, you're given r, and you're told to compute the quaternion. So let's say that the r is r11, r12, and so on. Okay, that is something we should be given, numerical values. There are actually two steps. The first step is to compute the magnitude of each component of the quaternion. So what is done here is, if you look here carefully in this equation, okay, so here, if you take the diagonal elements, you take this, and you sum it up, you'll see that you can actually solve for Q0, Qx, Qy, and Qz. There's something which I had not told you. The sum of Q0 square, Qx square, Qy square plus Qz square is always 1. The norm of the quaternion is always 1. That fact can be used in order to solve for Q0, Qx, Qy, Qz. And then you need to take the square root. Now what happens is, this is where the problem really is. When you take the square root, you have a positive square root and a negative square root. Because of this, computing the quaternion from the rotation matrix is non-trivial. So the steps which you use is, you first get Q0, Qx, Qy, Qz, the magnitude. The next step is, there are actually 4 cases. So that's 1. You see if Q0 is largest, right? You've already found Q0, Qx, Qy, Qz on step 1. If it's largest, then this is the way to find Qx, Qy, Qz. So you'll ignore Q, you'll ignore all the other values. This is the largest, you'll ignore all this, but you use this formulas to compute Qx, Qy, Qz. If Q1 is largest, then you'll go with this. If this should be Q, X, my bad, X. This should be Qy, and this should be Qz. 3 and 4. Anyway, so this is just something which you need to do, because you will see that the quaternion, this quaternion, and this quaternion, with everything negated, is the same rotation. And so you need to choose one of them, and that basically causes this confusion, or it causes this non-trivial way of computing the quaternion given the rotation matrix. Okay, so I'll add this to the notes. Now the last thing we'll be doing, and this is kind of the key thing, is that if you're given the Euler angles, like go way back and you need to find the quaternions, there's a way to do this. So if the Euler angles are phi, theta, and psi, then you can write a rotation matrix like this, right? We've seen that, nothing new. If you want to compute the same rotation matrix, well, in terms of quaternions, this is what you do. You write quaternion Q1, Q2, Q3 corresponding to rotations about X, Y, and Z. Okay, so how do you write that? Well, you have rotation. First one is rotation about x-axis by an angle phi. So Q1 is, here it's using the axis angle representation. So this is cosine phi divided by 2, sine phi divided by times I, because the unit vector is actually, in this case, a rotation about x-axis. Q2 is rotation about the y-axis by an angle theta. So you write the axis angle representation, and same for Q3. And once you do that, if you take the quaternion product, the formula I wrote down 2 times, first you do Q1 times Q2 and then Q2 times Q3, you'll get the equivalent of the rotation matrix. So once you get that, if you want to convert that formula to a rotation matrix, you go back one step over here, right? You'll get that quaternion, you can convert that to rotation matrix. So you can verify if this computation is right by converting this quaternion into the rotation matrix. Or you could do the other way. If you have the rotation matrix, you could convert to the quaternions and see if you get the same answer. Okay, so here is the summary of everything we've talked about. We have 4 ways of representing rotations. Okay, R, rotation matrix, Q, quaternion, Euler angles, phi, theta, psi, and axis angle. Now, some of these conversions are easy, some of them are hard. If you're given Q, Euler, and N, phi, so axis angle, all these can be converted to R, not a problem. We've seen formulas for all these conversions. You can convert the rotation matrix to Euler. This is something which I did not discuss here, but your homework too, there's a question where I've given you the rotation matrix and I told you to compute the Euler angles and I've given a hint. You can do this conversion, it's super easy. You'll do it for your homework. R to quaternion is complex. the one I showed you where you had these two steps, but it can be done. And then Q to N psi is easy both ways. So the key thing here is that if you want to do any conversion that is, let's say R to N psi, what you want to do is you want to go through either the quaternion or the rotation matrix, because you can do this conversion either way. You could go from R to quaternion, quaternion to R, or even R to Euler. The reason why you don't want to go through Euler is because there's a gimbal lock. So if you always go through the quaternion, you're safe. So let's say you're given N phi, and you're told to find the rotation matrix. First, you will convert that N phi to the quaternion, and once you have the quaternion, go to the rotation matrix. If you're given the Euler angles, and you're told to find the quaternion, what you want to do is you want to convert Euler to the rotation matrix, and then the rotation matrix to the quaternion. So the rotation quaternion is the best. Is probably the key thing which connects the bridge. So it's sort of everything can be connected to everything else by doing the R to quaternion conversion. Once you do that, everything X can be connected to everything else. So what I'll do is, for the next homework, which I'll post, you'll actually get some practice into this as to how to do these conversions. You'll write the formula. I've written down, I've given you my notes. You can use that. Feel free to use ChatGPT or any other AI software to get these formulas. And then just try to sort of be able to write these conversions is kind of important, because what will happen is when we use MuJoCo, we'll start off with Euler, but then sometime you want to go to quaternion because we want to do the math. But then Euler angles are nice for visualization. So we'll just be moving around through these different ways of representing rotations. The most common ones are going to be the quaternion and the Euler angle. Euler angle is good for visualization. Quaternion is great for the math. And then the bridge is basically the rotation matrix, helps you to connect them.